We've arrived now at describing the interparticle fluxes. These are then used to define particle motion. The lepton-quark conversions, the Holy Grail addition. Lepton-quark conversions are located at the base or beginning of the particle flux motion interaction tree. This presentation may help end the decades-old quest by investigators for foundational definition of lepton-quark transitions in particle physics theory. Now let's look at the lepton motion mechanism for the electron. At 0 Kelvin temperature, particle motion is zero, although quanta continue to circulate in the electron and proton bit cycle. At higher temperatures, particle motion occurs when quanta move from a source bit cycle to a destination bit cycle. Often the cycles are located in different cubes. The lepton motion mechanism is simply a sequence of two lepton-quark fluxes. Here we have the electron moving down, say, to a right-handed d-quark of the red variety, and here we have this transition in the next spot cube to an electron spot. For the electron, this flux sequence is simple quantum motion, and additionally, the beta decay definition. If the source electron occurs in a neutron spot cube, where we write the neutron breaks up into a proton and electron and a anti-neutrino of the electron variety. So our schematic diagrams here show the lepton motion mechanism, where we have two fluxes from electron to a d-quark spot, and then the second arrow from the d-quark spot to an electron spot in the next spot cube, which we have to imagine because it's not shown here. Same thing with the positron motion mechanism being a sequence of two fluxes. This case illustrates the expectation that all allowed particle interactions may be added to extend the flux motion tree, namely that all bona fide observed particle interactions can be derived from first principles. This is much better than the conventional view of particle interactions, which are sort of defined on an ad hoc basis and used to define fundamental forces as we discussed above. The positron destination spot units also represent the mechanism of lepton motion and are part of the source spot cube proton bit cycle. These data present an electron-positron difference which particle theorists may examine regarding physical significance. So here we have the first set of particle motion mechanisms for leptons. Moving on to lepton-mediated proton motion. The two lepton-quark fluxes may also be sequenced to exhibit lepton-mediated proton motion. For example, the x-axis DRR spot unit energy quanta moves to the electron spot in an adjacent destination spot cube, which by further unconditional bit motion may move to a DRR spot unit in the same destination spot cube. Here we have the DRR quanta fluxing to another spot cube in the electron spot, which then within that spot cube may flux to a DRR. Notice that color is preserved in this lepton-mediated proton motion mechanism. In the example, we had the DRR to the DRR. As previously reported, each spot unit in the positron spot participates in a different proton bit cycle. Thus, the positron may play a very special role in multi-nucleon atoms. Consider a quanta in a proton cycle arriving at a positron spot unit. If this energy quanta moves to another spot unit in the same positron spot, It transits from one proton cycle to another in an adjacent spot cube. In short, this positron-mediated proton motion mechanism favors concentration of energy in neighboring spot cubes, essential for multi-Z atom nucleus formation. So it's party time in nuclear physics. The so-called force binding nucleons to form multi-nucleon atomic nuclei and ions has been called the nuclear force. The positron-mediated proton-nucleon motion mechanism described above would clearly favor nucleon formation in spot cubes adjacent to existing nucleon spot cubes by feeding energy quanta into the adjacent spot cubes. This process might be crucial for nucleus formation. That is, this single mechanism may account for most known phenomena in nuclear physics, and thereby may become one of its most central fundamental principles. How about quark-mediated proton motion? Quark-antiquark fluxes may mediate proton-nucleon motion where the destination spot unit is located in a different proton bit cycle than the source spot unit. This quark-mediated proton motion is only shown by half of the arrows above here, the ones highlighted in pink and green. Here we have a quark, quanta, moving to another spot cube, here and here. But you see, not this one, and not this one. Same thing for the matter quarks, transitioning to an antimatter quark in another spot cube, as was shown here and here, also in the green arrows. So now we've described lepton-mediated proton motion and quark-mediated proton motion based upon our particle flux and motion tree. How particles move. Particle physicists have used the classical regime based on belief in continuous space-time to describe particle motion, acceleration, trajectories, etc., including effects of electromagnetic fields. What has been glaringly missing is how particles move, as if description of observed particle motion was good enough. Sorry, it isn't. To put it bluntly, almost anybody can see things move and make measurements on motion distance and other parameters, but the business of physicists is to describe how things move. Binary Mechanics Lab puts the particle flux and motion tree on the table for consideration. Why are other labs so far behind Binary Mechanics Lab in dealing with physics, namely how things move in this presentation? Anybody know? Maybe others are more concerned with tinkering with super powerful, super cooled magnets in underground tunnels. Who knows? They did not expect that BML would win in producing so many milestones. All the polls said the physics cartel was going to win.